the other part about methodology, because going back to more of the basics, the same questions arise, and this is good. That's good timing because this will actually go back a little bit more to fundamentals of how do we do this properly. Yeah, okay. So chapter 11 of the deep learning textbook has a discussion of some of these methods as well, which is interesting to look at, right? Because no matter what you're doing, if it's whether a simple model or a complicated model, you're going to get to these same problems of how do you choose all the numbers, how do you make it work more effectively. So chapter 11 in that textbook has a bunch of useful ideas that come from a lot of the stuff we've talked about, right? You have to know your data, so to try to understand what your data is about and what your task is going to be. But you have to define your goals of what you're trying to evaluate very clearly, right? So it has to be something that's verifiable, right? That you have some metric to evaluate it. You know, like, is it that you're trying to maximize accuracy? Is it trying to maximize efficiency? Is this going to be running on a cell phone? Is this going to be pre-processed ahead of time? Or does it be something that can handle new data arriving over time? All these things kind of affect how you would design the model, right? So it's different things here. We're trying to target different aspects, right? So inception, these very deep models we're trying to maximize accuracy, right? Because they were on a competition, right? Maybe that's not your focus, right? Maybe you just want something that's going to be pretty good but very fast once it's trained, right? So you actually want a very shallow model, or something else. So they have a bunch of tips here about how to build that comparison and practically how to train a network, but also just design it, right? So it's good advice to say, like, build the simplest one that's going to work first, and then make it more complex depending on what you actually need. But to do that, you need to know what's possible, right? So should you add this kind of new component or not, right? So it's good to have baselines. So the stuff we've talked about previous in the course, right? I mean, logistic regression, SVM, random forests, those are all very powerful models. So you should be comparing to these other models for your task, because maybe a deep neural network's overkill, right? Maybe something with fewer parameters that doesn't introduce as much kind of choices is going to work just as well, and neural networks kind of overkill, right? But you know, if your problem is complicated enough, deep learning is usually going to beat it if you set it up the proper way. It's just a matter of how long you'll have to work on to do it, right? So these are all important things to look at. Obviously, the structure. So if you have spatial images or time, you have to have these kind of different components. But you've got your fully connected, your convolutional, and your recurrent components now, which can be matched kind of as needed. And then they talk about, which is some good advice actually, about creating multiple baselines, right? So create, you know, your own fully connected baseline network that just takes inputs and outputs and works for the problem you're tasked on, right? So like they're saying here, 3 hidden units with RLU and Atom optimizer. These are all a good way to set things up. Batch normalization is a thing we didn't talk about yet. It's described a bit in here, so it's a good thing to look up as well. I can add it into next week's stuff. It's just another trick, essentially, to improve the stability during training by normalizing the weights from each layer as they're coming out, right? So we actually talked about this at one point with whitening and doing like the standardization, normalization of data. Sometimes it's used before PCA. And you kind of center the data and kind of normalize it so that its variation is within a certain range. Batch normalization, you do that on a per layer basis, and so every layer you kind of renormalize it so that its outputs stay within some range, and then they don't veer off into, very high or low numbers, because everything's relative in a neural network, right? It's about whether this input feature is more important than that feature. The actual numbers here don't really matter as long as they're all scaled in the proper way. You're really trying to pick out the important features and create essentially new subspaces at every one of these layers. We talked about dropout. So that's your fully connected baseline. If you have images, you'd have a baseline of a kind of a standard convolutional neural network, like we talked about, with a few convolutional layers, and you have to choose your optimizer. If you want it to be deeper, you can use these ResNet things, but if it's not that big a problem, you don't need to. If you have time, then you can add these LSTM nodes we talk about. There are other kind of variants of these, but that's kind of the standard one, and it's not simple, I agree. But it's the mechanism people have found to kind of at least work in some sense. Because if you just put links to the past and put it in there, it doesn't work very well at all. You need to have some kind of ability to filter out data that is being remembered and is being forgotten. Right? So there's a different view of that LSTM node I was showing, where there's an explicit forget gate, essentially. So this is a weight that you're learning to say that data should not be remembered anymore. So I wanted to find that other thing because there's a couple things you could train them, right? Like you could test for, trying to decide on what these parameters should be, like how many layers you're going to use, what size should your filters be. Each of those is kind of its own experiment. You have to kind of test and analyze. So increasing depth usually helps, but at some point the improvement doesn't help that much, right? So you have to kind of decide when to cut it off, right? So this can be done when we talk about train, test, validate, right? Your validation set is something you could use to try out different hyperparameter settings to see when to stop, right? This kind of assumes you have a lot of data, so that's why the really effective things are dealt with on very large data sets like image data sets and text corpuses and advertising data. Because at some point you run out of validation set to play with. What do they have, right? If you're doing badly on the test set, you can do regularization stuff that we talked about, like adding dropout, that basically helps it become more robust to the data. You could also do augmentation, like we talked about, basically trying to increase your data set size if you can't actually get more data. Because if you have more data, then you assume you're going to get better performance, right? Error training examples. Yeah, okay, so I was trying to have a capacity graph. We talked about capacity kind of long ago when we were talking about train, test, and validate. Right, we're talking about the capacity of a model is how many things it can kind of classify in the problem, right? So what do we have here? We've got our training data is the blue line, which you can't see, it's really low here, and it's basically improving, and at some point it gets to a maximum and just stays there. And this dotted line in purple is the Bayes error, so it's kind of like almost not the optimal you can get to, but the optimal you could get to with kind of independent assumptions amongst the features. So you should be able to beat it, but maybe it's near your optimal. And then they have their test and their training data, performance, right? And so on training, obviously, you'd hope your error would go to zero because you're going to perfectly overfit and perfect your model on the training data. And the thing you watch then is your test data. So you can look at your test curve, and they show different, like, I guess you could plot your test curve on a log scale or a quadratic weighting, and plot your testing performance, which would be, as we've discussed, I guess your validation performance. But if you didn't have a validation set, you'd just be doing straight on your testing, and deciding when to stop or which model to take, right? If you've already tuned everything else, you could be doing this on your test data. If you're trying to tune your hyperparameters, you should do it on your validation data. And this curve would be your validation curve. But you want to watch for these points where it gets worse, right? Where the data you've never seen, the error is going down, and at some point it goes up, right? And so what you really want is to pick these spots in the middle where it's at its minimum and you haven't completely overfit on the training data yet. But that's the goal, right? And so, but then for every one of your hyperparameters you're trying to choose, this is a thing you could do. So in the book, they have a bunch of, like, a table of different things that you could train, and what the outputs would be, like what you would expect the performance or result to be of changing that, right? So if you're changing your number of hidden units, it's going to give you more capacity to fit a more complex model, but it's going to take longer to train, right? So it's a trade-off. Learning rate is an important one. So some of these other ones about the size of the filter, you can imagine what they're going to do. Learning rate's important, and they do mention this as a really important one. What is a learning rate? It's a learning rate is the alpha, like the step size, right? When you're updating that gradient, remember you've got your current weights, and then you've computed the gradient through backpropagation. You've got a gradient now for the whole thing, and you're going to update the weights. How much do you weight them, right? The gradient's got its own scale, and the numbers, the outputs of the weights have their own scale. But you have to decide at some point, should you just create a small update? Should you create a large step size? So that's very particular to the domain you're working on, or how the data works out. But this learning rate determines basically how much you listen to the gradient every time you train it, every time you run a backpropagation step. And if the step size is too small, your network's going to train very slowly and take forever to get anywhere. If you make the step size bigger, it'll improve quickly, but at some point it'll get suddenly worse, right? Because what will happen is you essentially overshoot, right? This happens in optimization as well. You might have the weights that are kind of really good for doing something, and then you got as close as you could. The step size is like 0.5, say, right? And then you got really close, and now the update on the some of the weights are more than 0.5, but the optimal answer is like 0.1 away on a lot of the weights. And you don't know you're near the optimal answer or like a really good answer. So you're taking steps of size 0.5. You're just going to jump around it forever, right? You're never going to actually hit that thing unless you randomly get lucky. So a smaller learning rate would work there as well. So they'll often do like decaying learning rates. So you start it with fairly high to move in, and then you decay the learning rate some weight, so that it finalizes and just fixes on one thing. So like simulated annealing is another method they use in kind of more classical approaches, and you can essentially do the same thing. You're just turning down the temperature until it stabilizes. But now you've got a new parameter. What's the rate of temperature decrease of that? And there's no right answer to that either. But that's a very important one. Just say that the first thing to tune is the learning rate, and then there's other ones you can use. And then for the actual parameters, like how many layers to use, what size convolutional filters or things like that, rather than just searching for all the values, you want to have some kind of methodological approach. This is where I'll stop, to changing them. And the straightforward thing to do would be, say, take a grid search, right? So pick the range you want to try, and you want to try neural networks from size 3 layers to 20 layers as a reasonable thing that we can afford to train. And so I'm going to train it on 3 and 5 and 10 and 15 and 20, and then I'll search in between and figure it out, right? So you could do a very structured grid search. So this many layers deep, this size convolutional filter, and search for it. In the text, they actually kind of say that the random one, doing a random approach is actually more effective because you're not going to waste your time looking in a place that's really useless. So you can randomly search this space and then maybe focus in on the areas that are more promising. So if some area seems to have a certain more values that seem to be worthwhile, maybe you sample next time nearer to that, right? You can reset your sampling, like particle filtering. You essentially focus in your sampling to a different area of the space. But this space we're searching here now is the hyperparameter space of your network, right? How many layers, how many filters, learning rate, other things like that. And it's just this iterative approach. So there's no right answer. There's anyway, they have an entire chapter on advice that people have. They do have, at the end of that chapter, a discussion of, what is it? Automated ways of doing it, which people can use as well. Oh, no, I'm on the wrong chapter, sorry. There are automated approaches that, well, I'm in here, that's why. That try to do that automatically, but they're still doing search. So they try to turn the weights of a network into an optimization problem and then search that. So that is an even more computationally intensive thing, but there's definitely some impressive things happening there. But at the basic level, when you're doing your own network, those are some kind of approaches. We're using all the same things we've learned about how to make those choices. So I'll stop there and then see if people have questions, although we're over time now. So let's, what other questions do people have here? Can people see that? Oh, okay, it just switched. Let me go back to, here, this table's the best thing. Okay, so last question someone had, are all the hyperparameters equally important? Yeah, I guess, yeah, I don't know. There are some that are more important, right? So like they're saying learning rate is very critical because it affects everything in the way you learn. So that's a major thing to decide how to do properly. The higher level parameters, obviously, about architecture, right? So whether you're going to fully connected or convolutional or whatever, those choices have to be kind of decided before you can really even do a lot of those choices. But things like, whether the convolutional filter is 3 by 3 or 5 by 5 don't seem to be super important because people try different numbers and they get kind of somewhat better results. Much larger filters don't seem to work, so maybe that's a less important one. These things like padding and other stuff around the outside of the network don't seem like they're important. They need to be there in some sense, but what number it is going to have a huge effect. Dropout can have a big effect, but maybe it depends on how complex your data is. So if you have a lot of features where all the features are super important and very independent, I would think dropout, I don't know, I would think dropout wouldn't be that useful as much because every little piece of information is highly useful and correlated, and you're often going to have to work it out, right? So if you want to have a high dropout rate, right, so we're randomly knocking out some of the weights while we're training, then that kind of assumes that you could often get by with ignoring a whole bunch of the features, right? So if you know that many of the features are basically correlated strongly, say in economic, financial data or something, like they're all in the same market, the same industry, basically they're all interrelated. There's just small variances between each company's information and what's relevant. Maybe a high dropout rate would still be useful because you could learn just as good a model, right? Yeah, Professor Alex Wong in system design in our university has a neat set of methods where they train fully connected networks on some problem, I think medical images or something like that, with quite a few fully connected layers and fully like deep. And then after the fact, they try to knock out the weights and remove them entirely, and then say how much impact does that have on the accuracy, right? And every weight you drop out, you're going to basically improve the speed of the model at runtime, right? And so it gets faster and faster, and their accuracy only goes down a tiny bit because some of those weights, some of the arcs in the network are not that important, but you have to figure out which ones to use. So they randomly search through that and then optimize the accuracy by dropping some of these weights, and then they get a model that's like 100 times faster on runtime with similar accuracy by doing this post-processing step. So that's related to dropout, but I just thought I'd mention it because so like we said in the presentation part, you should know upfront what target you're trying to hit, right? What's your accuracy level you're aiming for? What would be good enough? And then you try to tune enough of these things so that you get close enough to do that. If you're doing research, then you're trying to figure out a way that makes a dramatic improvement in one of these things, either for speed or generalization or accuracy. If you're doing it for industry and applying it, then you really just want to take the ones that have been shown to work and follow kind of the order of parameters to tune to get to the quality you need for your task. Okay, so I'm going to stop there. So we're over time, but thanks for listening.